The subject of this demonstration is the well-known Puma260. This is a small robot with a maximum reach of about 500 millimeters. It is equipped with a controller running VAL, its programming software. We at the Center for Intelligent Machines, SIM for brevity, replaced VAL with RCCL, the Robot Control C library developed by Professor Vincent Hayward, also of SIM, to implement our minimum time trajectories for pick-and-place operations. A pick-and-place operation is a task in which an object is displaced between two finitely separated locations, which are called poses, positions and orientations in the robotics terminology, in such a way that the object is picked up at rest and then deposited at rest as well in a different location. Typical robot trajectories programmable with VAL produce a uniformly accelerated joint motion until the joints attain a pre-assigned maximum speed. Then the joints coast for a certain period and finally decelerate uniformly as well until they reach their goal position. These motions thus invariably entail acceleration jumps from zero to a finite value and vice versa, which then leads to shock and vibration at the beginning and the end of the trajectories. Such velocity programs are called trapezoidal because of the shape of their velocity versus time plots. The effect that we observe in these views is due to the sudden arrest of an object, similar to the crashing of a car against a lamppost, a phenomenon that is known in mechanics as impact. The repetitive impacts to which a robot is subjected damage its bearings, its motors, and its overall structure. Notice that trapezoidal velocity programs are overall slow but nevertheless shocking. One way to eliminate jerky motions is by properly programming smooth joint trajectories. Various types of motion functions are available for this task: polynomials, cycloidal motions, and splines. We opted for cycloidal motions because of their simplicity, but other functions could have been used. Cycloidal motions begin with zero velocity and acceleration and finish likewise. If needed, a coasting period can be smoothly blended into the joint trajectory. The form of the cycloidal motion allows to predict the value of the maximum joint rate to be produced. By programming the motion in such a way that the fastest joint is driven at its maximum rate, we can attain minimum time trajectories. We call these trajectories near minimum time because of the limited function space in which the optimum is searched. The motion implemented on the wrist can also be jerky, but this motion can be readily smoothed by proper motion programming. With these experiments, we have shown that fast motions need not be jerky, which can be attained by proper motion planning.